In this session we are going to look at electrical power, and we know that power is defined as the rate at which we transfer energy. In physics, transfer of energy is called work, so the rate at which we transfer energy is the rate at which we do work. Rate of basically means divide by time, so power, work done over time. Let's imagine we take the potential difference across a component and we multiply by the current through the component in an electrical circuit. We know that potential difference is defined as work done per unit charge. Think back to the definition of potential difference in lesson 1 in this topic, and we know that current is rate at which charge moves around a circuit, Q over T. So potential difference, W over Q, work done per charge. Remember, a volt is a joule per coulomb, and current is rate of flow of charge. Well, when we multiply those together then, what's going to happen is that the charge will cancel. What we'll end up with is W over T. In other words, rate of doing work. We've determined the power. So if we multiply the potential difference across a component by the current through it, what we are going to determine is the rate at which energy is being transferred in that component, and therefore we're going to get the power that is dissipated in that component. Power is measured in watts, capital W. So we've got a formula there, P equals V times I for electrical power. But of course we also know that V equals I times R, the relationship between potential difference, current and resistance there. So we can replace, if we want, we can replace V in this formula with IR. And if we do that, P equals IR times I, it'll be I squared R. So we've got a second formula for electrical power, and indeed we can even rearrange this formula. I equals V over R. You replace I in this formula with V over R, you're going to get P equals V squared over R. We have another formula here calculating electrical power, which you will find in your data book. So basically we need to know that power, the energy transferred per second in a component, voltage times current, or I squared R or V squared over R. Of course, once you've got the power, if you want to know the total amount of energy that's been transferred in that component, the total amount of work done, all you've got to do is take the power and multiply by time. So the energy transferred during a particular time in a component will just be V times I, get the power, and then multiply that by T, and you'll get the energy transferred over time T. So we've got a simple problem here involving electrical power. We have a filament lamp. The lamp is rated at 3.5 volts, 0.7 watts. Now what that means basically is when you've got 3.5 volts across the lamp, it will be transferring 0.7 joules of energy into other forms, electrical energy into other forms every second. Okay, so that's the power that it's dissipating, provided you've got 3.5 volts across it. At that time it'll be lit to normal brightness. We want to first of all find the current in the lamp. How could we do that? Well, we know that electrical power is voltage times current. So here I've got the power, I've got the voltage. What we want to do is to find the current. All I've got to do is say, right, okay, 0.7 watts is 3.5 volts multiplied by the current. So the current, 0.7 watts divided by 3.5 volts. And what you will get is 0.2 amps or 200 milliamps. During a 5-minute period then, how much electrical energy will be converted to light and heat? Well, we know that power work done over time, so work done, the energy transferred is just power multiplied by time. Here we're dissipating 0.7 watts of energy every second in this filament. 5 minutes, well, don't forget a watt is a joule per second, not a joule per minute, it's a joule per second. So we need this 5 minutes in seconds. Every minute has got 60 seconds in it, so we've got 5 times 60 seconds. And if we multiply those together, we're going to have 0.7 times 300. And that will give us 210. Of course, the unit of energy is the joule, capital J for joules. And there we are. Simple problem involving electrical power. They could have asked us here, rather than working out the current, they could have asked us to work out the resistance. If we'd got the power and the voltage, could we have got the resistance? Well, yeah, because we know also that power equals V squared over R. So if we'd have been asked for the resistance instead of the current, we could have rearranged this formula. R will equal V squared over P. We know the voltage. You know the power, you could then work out the resistance. And that's 18 ohms, 2 significant figures. Okay, well what we've got is a circuit setup here where we have 2 pieces of resistance wire, and they are connected in parallel as shown in that circuit diagram at the bottom left. We've got a variable voltage power supply. Now if we zoom in here, we can see that actually the bottom wire is much thicker than the top wire. So although we've got two wires connected in parallel, they are the same length, but one of them is thicker than the other, and that's the lower of the two wires that you can see here. Now what we're going to do is we're going to turn on the power supply, and the question is, in which of those wires are we going to have the greatest power? Which of those wires are we going to have more power dissipated in? Have a think about that. Pause the video. And when you think you have an answer, play the video on to find out. So here we turn on the power supply. As we turn that on, what we can see is the wire at the bottom, which remember is the thick one, begins to glow red hot, whereas the wire on the top remains relatively cool. So it's the thick wire here that's getting hotter, that is dissipating more power. Can we think why that would be? Well, we know that power equals V squared over R. You see on the bottom here, power equals V squared over R. Of course, if the components here, the two pieces of resistance wire, are connected in parallel, then they will have the same potential difference across them. V will be the same for both wires. We know that idea from GCSE. We'll look at that in a little while when we get on to doing circuit laws. But if they're in parallel, V will be the same for both wires. However, the thicker wire, if they're both the same length and made from the same material, the thicker wire will actually have less resistance. Remember, R equals rho L over A. Both wires here are made from the same material, therefore they have the same resistivity, they have the same length. Rho and L is the same for each wire, but A is larger, the cross-sectional area is larger for the wire on the bottom. If we divide by a larger value of A, we will get a smaller value of R. Less resistance for the wire at the bottom, go back to P equals V squared over R. V squared is the same, R is smaller. Divide V squared by a smaller number, you will get a larger power. So more power here is being dissipated in the wire on the bottom. It's hotter. Now what we're going to do is we're going to change over the connections. So rather than now connecting these wires in parallel as they were before, we're now going to take the same two pieces of wire, but we're going to connect them in series, end to end. I want you to think again, which wire now will dissipate the greater power? Pause the video, have a think, try and think of an explanation. And then, when you've got an answer, play the video on and we'll see if you're correct. So here we are, we've connected them in series. We're going to now turn on the power supply, turn up the voltage a little bit, and hopefully you can just see now that the thinner wire is the one that is beginning to glow. The thinner wire is getting much hotter than the wire at the bottom, the thicker wire. So the thin wire is hotter than the thick wire when they're connected in series. Why is that? Well, this time we can use the idea that P equals I squared R. The current here is the same in both wires because they're in series. So the wire that's going to get hotter this time is the one with the larger resistance. Now remember, R equals rho L over A here. So the thinner wire, smaller value of A, is going to have a larger resistance because P equals I squared R. I, and therefore I squared, is the same for both wires. That means I squared R will be greater for the thinner wire with the greater resistance. So therefore more power is dissipated in that wire, gets hotter, and that's why we see here it's glowing red hot.